And more importantly, when we talk about performance, often you might feel like you're trying to find the needle in the haystack, right? You're looking and trying out a bunch of things that might work. You may have read about it on a blog. You may be an expert and actually think that you've got the right answer. What I'm here to share is a couple stories around how you can really get insight from an end-to-end view into your application, really running on top of Cassandra, or we'll take a quick look at MapReduce as well. So if you're dabbling in Hadoop, perhaps you're running MapReduce on top of DataStax, which happens to add that layer on top of Cassandra. We'll give you some insights and some best practices on how to take that holistic view. And at the end of the day, what we're seeing with any Cassandra, NoSQL database, even Hadoop, it's a level of complexity that you're adding. Some of you may be working on a brand new project where it's pure Python and Cassandra, but I would guess most of you are adding Cassandra into an existing application. Maybe you're looking to kind of take an expensive transactional system and reduce cost, increase efficiency with something like Cassandra. So at the end of the day, you're looking at the needs to kind of pull together different views, and the transaction, while it may end up in your Cassandra cluster, probably started somewhere else. So getting insight into where things really come from, the complexity that is probably reducing the visibility into your app, and how do you close that gap so that you've got sort of that end-to-end view into what really happens and what matters. I know there's a couple of you here that are just getting started, and I'm not going to try to pigeonhole Cassandra in one slide, but I want to kind of, from a perspective of performance and what it's good at and what it's not good at, because that'll lead into the discussion today around our kind of case studies. Cassandra is great when you talk about something that provides fast read access or fast write access, right? You don't necessarily want to read and write, or write and then read at the exact same time, at the exact transactional level, but it's great at taking those core concepts, scaling them horizontally, and as you saw Jonathan earlier today, a really great linear scaling, so you can add more servers to really increase your throughput. Of course, it's got redundancy and high availability built in, but it also needs you to have some best practices and some patterns built into your design. You want to make sure that you've got fairly even distribution of data. That way, when your requests come into the cluster, you're not seeing largely different response times, be it on reads and writes. We also want to make sure that when you have applications that have maybe a poor pattern of access, for example, a single request from your application triggering 4, 5, 10 requests to the database into Cassandra, you want to know about that because it's not necessarily a Cassandra issue, it's more, is your application doing the right thing? So how do you get insight into what your apps are really doing? Looking at those patterns that are a best practice that if you start with the right approach and you can kind of enforce that through your development, you'll have a much better experience in scaling out your Cassandra infrastructure. When we dive into Hadoop, we'll talk a little bit about the world of batch processing and being able to take requests that are ultimately driven across the cluster, run in parallel. And there's some unique things that happen when you think about a batch workload versus a transactional workload. Specifically, little things that go wrong, get really wrong as they start to scale across the cluster. So, of course, Hadoop is great at, and not so much Hadoop in general, but we'll talk about MapReduce, since MapReduce does run on top of DataStax Enterprise, and so you can leverage that data that resides within your Cassandra cluster. What works well, and what are some of the challenges? Specifically things like distribution of data within MapReduce, wasting resources when you think about what's efficient and what's not efficient. We've got a case study with an application that one line of code loading a string library to compare data objects had a massive impact on performance, something you would never think about from a development perspective until you actually see the impact running in production. So it's those types of things that really give you insight into how are people really building the application that runs on my cluster, runs on my environment, and then being able to make the best decision, be it performance tuning, scaling your database from there. Let's start with one of our ad tech customers in New York. So this is a company that I believe there's even a couple of you that are in the ad tech business here as well, serving up ads, looking to find the best match. This particular company was really about trying to match you with your peers and your friends, so that when that bid request comes in to say who's got the best ad for a customer, they've got the ability to very quickly pull everything they know about you as well as your friends to deliver that. And if you're not too familiar with what a real-time bidding network looks like, the request comes in, you load your browser, and everybody's seen those ads on the side. There's a exchange that is essentially bartering that data to say, who's going to pay me the most for that impression? And of course, you need to make that decision as fast as possible. Milliseconds matter here because you're going to need to decide whether it's worth my client paying X cents per million impressions to put that in front of the end customer. So the request comes in from browser through an exchange. ultimately hits somebody who's in charge of selling and brokering ads on behalf of their customers. And then that analysis takes place very quickly. And so the use case of high-speed availability on that type of data, the impression, the graphic, and the targeting is really what we're looking at here. Of course, there are some things in place that really drive whether you're going to win and make money for yourself or for your customers, and that's all about how fast can you profile that user coming in against the data set that you know about it. So they chose Cassandra for a couple of reasons. One, high-speed, low-latency access. They wanted to make sure that when those requests came in, you don't want to be serving the same ad to the same person, so you want to keep track of everything that you previously served about that person so that you can get the most interactive type of participation. But you also want to kind of be able to segment them, try certain offers, certain products. So a fairly typical use case, and of course, low latency. In this case, they had about 100 millisecond SLA with the brokerage, meaning if they don't respond within 100 milliseconds, they lose, they don't even get a chance to bid. This isn't a database requirement, this is end-to-end system. 100 milliseconds is really the operating window. So when they looked at Cassandra, they said, well, we're going to try to follow best practices when we build out this data schema because that's important. Cassandra was the right fit, but also they had the right space around data. So they said, well, it's mostly schemaless. They know the type of data they're going to be expecting. They're going to do mostly writes because they're going to see all the requests that are coming in. And when they need to read, it's going to be outside of a read. So it's never going to be a transactional. We're waiting to kind of get back the data that we just wrote into Cassandra. Optimizing around different types of put and get, never doing a scan across the data. So they'll pre-process the type of profiles for a user. And so all in all, it looked like a pretty good fit for Cassandra. And then denormalize the data as it comes in so that it's ready to access on the way out. Looks pretty good so far, and of course trying to optimize each step of that transaction. So when you start to tune your cluster, there's some best practices that you can find. You can go through and denormalize data is one that you'll hear. Make sure that you've got multi-column keys set up. You'll have distribution across different nodes. And more importantly, you'll try things like, well, does compression help or hurt? Does it make a difference whether I've actually got it enabled? And depending on your use case, it's going to vary. And also the type of goals that you have as far as how much data is actually in there. And there's a variety of disk cache settings that can be set. And in general, it's kind of a trial and error process for a lot of people figuring out, well, does this work? And so this particular customer went through and tried a bunch of things, but at the end of the day, they still ran into a few problems. Caching didn't necessarily solve the problem. Mem tables and everything that they tried to do in front of other parts of their application still left them with some critical things. One, they were missing some bids. So that 100 millisecond SLA that we talked about, they still didn't know exactly why they hit 110, 150 milliseconds on some of those requests. They could see see the requests coming in and out of the cluster, but it didn't necessarily give them insight into, well, I've got more than just a request into the Cassandra node. I've got some processing that happens in flight before things come in. So they need to get visibility into really from the requests that came in from the exchange throughout their system into the cluster and figure out why were those occasional bids being missed. Everything they designed is supposed to be ultra efficient. They saw their query times, for most queries in the 10 to 20 millisecond range. So relatively fast, and what you would think would be enough buffer for the other 70 to 80 milliseconds of everything else that happens within the system. Occasionally they failed. Occasionally they actually didn't come back. You heard this morning a couple of reasons, and there are some edge scenarios in Cassandra where things will actually get locked up in the cluster. If you're waiting, for example, on a consistency of all, there's a good chance that if something gets backed up in queue, you might actually time out before you can get the request back. So little things that come down to data access patterns around the application, even if you don't think you're doing it, as you actually look at how the application is really accessing a cluster, you discover those things very quickly to say, that's really what happened on this stalled request or this transaction that timed out and came back with an error. And then lastly, looking at variances. Why do I see 10 to 20 milliseconds on average, but every now and then 40, 50, 60 milliseconds coming back from the cluster, which ultimately ends up driving the overall transaction time above that threshold. So trying to understand the outliers in basically this system that is designed for real-time access into the bidding network. So how did they get there? How do they start to resolve these? Well, they started by looking at some kind of high-level metrics, things that you might get out of Ganglia, things that you might look at from an ops center if you're using DataStax Enterprise, to try to see that holistic view of how is my cluster doing? And nothing really jumped out at them. They read the blogs, they try to do their own investigation of, well, what's the type of tuning that I can do, and can I look at specific GMX metrics? Can I look at requests per second? Can I look at the number of column families in play, and trying to sort of do that triage, but still looking inside the cluster, which, as it turned out, wasn't necessarily the only story to look at, because as much as you think it's the database's fault, right, the reality is it's not always the case, and how you access and really how you build your application patterns determine a lot on the end-to-end performance. And of course, as we heard today, you should all be deploying 2.02 into production. It always gets better and faster, but the reality is there are regressions, and there are things that you need to check out. So just because you've got 2.0 or 2.01 or 2.02 doesn't mean it's going to be the best fit for your application. So being able to bench line between releases is important. And so having a process in place that lets you actually measure and know whether it's effective to be able to roll it out. So they started to look outside of the Cassandra box because they felt like they'd done the tuning, they felt like they had kind of pushed as far as they could into optimizing Cassandra, even though they knew there was some discrepancy in average read request time and some outliers where things would just be slow occasionally. So they tried to look outside and say, all right, can we take the transactions that are coming into Cassandra and look holistically end to end? Essentially looking for that black sheep that they knew was out there that was causing problems somewhere, but they had gaps, and they were trying to close that gap in visibility between what was actually happening in their entire application all the way out to the Cassandra node. So as you look at taking that view of what's actually coming in, there's some general best practices that you can apply from the performance management world and say, what's the overall response time? And then to start to break down each tier so that you can understand within your application where are the bottlenecks. And ultimately, if you're hitting 120 milliseconds and your target is 100 milliseconds or less, what happened in there? Where did you spend your time? And starting to measure each piece along the way to build up that end-to-end view. You also want to look at the data access patterns. How is my application accessing the cluster? For every transaction that comes in, do I hit Cassandra once, or do I hit it 5, 10 times? So in effect, even though my response times from the cluster is great, I'm actually looking at 4, 5, 6 building up to satisfy that end request. So understanding the pattern of your application as well as where that traffic's coming from. And then lastly, how is data distributed in the cluster? Is that affecting things? Because I might have data that's not as evenly distributed, and certain nodes have different characteristics. They're running in different data centers, they're running on different hardware, software, different network in between. So looking at data access patterns, and I mentioned earlier the consistency level. We didn't think that we were accessing things with consistency equals all, but if you are, how do you know? How do you find those to make sure they're not the root cause or the culprit? So as you start to look at the end-to-end view, you want to start at the very edge. So the data that's coming in, and if you can, even measure it from what does an end user see or what does the brokerage house see, so that you've got that perspective of they're telling me I missed the mark, I didn't get my request served because it returned in 120 milliseconds. So start there, understand what your either end user or end client looks like when the data's coming in. Make sure that if you have any third-party requests, in this case as part of their transaction flow, while they weren't hitting a Facebook login screen, and this is something where we couldn't share all of their proprietary details on how they built the system, there were some third-party systems that came in to collect and assess user data. Not everything was contained within Cassandra. That they kind of overlooked in their first step of measuring. The way to work around that is to say if you have third-party access that doesn't return, use that as your own metric. If you don't have the data coming back, move on. Don't fail just because you've got a third-party data service that isn't available. Looking at your own application infrastructure, trying to understand internally what do those tiers look like, where do transactions flow, and then more importantly, how do they hit the backend cluster? Are you going against anything beyond just a SQL server, beyond your Cassandra server? Are there other pieces of data that are coming and going? And that end-to-end view of your application, you've probably modeled it when you built it. It's probably on a whiteboard somewhere, but it's probably different when it actually lives in code. So getting insight into what's really happening inside your app is going to let you then explore what really contributes to that end-to-end transaction time. And then finally, of course, once you understand where my entry point is into Cassandra, I can start to look and say, is that really the bottleneck? And is that where my the culprit lies? So starting to calculate that, looking at purely the Cassandra side, the access pattern is important. So we mentioned a little bit around understanding how is your application interacting with Cassandra. You can do things like instrumenting each call to say I've got a certain IP address calling a cluster. You can build up sort of your own view. And there's also tools in place that give you this kind of visibility out of the box. So depending on how you're looking to kind of instrument your cluster, there's lots of different ways. Some provide a great fit for kind of rolling your own. Others can give you a view that really show you, based on each transaction that comes in, how many times am I hitting each service, and we'll go into a little bit more detail around this particular pattern where we saw some interesting behavior, something that was completely unexpected from their application. And as you start to look inside of a call into Cassandra, it's important. You saw today there's some tracing that's now built in where, in maybe an offline or non-production environment, you can start to trace individual calls. That starts to give you some insight into what's actually happening. I can see where the data is being pulled from, where the coordinator is sending each request. And it's going to give you that level down to be able to say, starting with, what's the query that's being executed? Where is the node that's going to supply the data for it? And then, things like consistency level, making sure that you check and the behavior that you're expecting is actually what you intended. So a starting point is to say, what's the query coming in and the associated characteristics behind it? What's coming back from each particular statement? What type of data are you returning? So if you have what should be a relatively short query, make sure that the data you're returning is not huge in size. I mean, you want to make sure you're pulling the right data. You don't necessarily want to return the entire row, depending on the type of data that you need. And then ultimately, how many calls are you making? How many requests within the cluster? Whether you're using tracing, whether you're using another tool that gives you that insight, making sure you understand the flow within the cluster, so that before that request is served back, you've got a good picture of what's happened within the environment. Again, data access patterns, all this kind of contributes to your understanding of the application running on top of Cassandra. So what we found looking inside is, in this particular case, the transaction coming in, even though it was one outside transaction, was generating about 5 calls into the cluster. 4 of those were coming back in 15 milliseconds, about what was expected. But there were a couple of them that were averaging 50 to 80 milliseconds. So if you're trying to achieve 100 milliseconds, having something like this happen occasionally is going to completely break your application. It's still going to return, but you're not going to be able to serve the needs of, in this case, a real-time bidding system. So being able to understand and get to that point where you have isolated, in this case, some external dependencies that might have been contributing where you're calling a third-party service. Inside the cluster, you've got 4 out of 5 that are working well, but one particular node, in this case, our third node is performing where we would expect, 15 to 20 milliseconds. The other 2 nodes are quite a bit higher, 50 to 80 milliseconds. Still not bad, but certainly not within the SLA we were expecting. And that gives you some insight into say, all right, now I can look at those particular nodes and say, really, what's driving the difference between queries when data is extracted from node 3 versus node 4 or the other ones. And getting inside to say, now we're one level down, we're in the node, and trying to understand whether it's through tracing, whether it's through using another tool, what exactly is causing that 80 millisecond mark versus 15 milliseconds. And being able to get inside the job and say, here's what's actually happening. Is it reading and writing from disk? Is it waiting on memory? Is it contending for some type of buffer that's in there? So getting to that next level down of really what's happening behind the scenes. Something that is relatively, can be relatively complex, but if you can isolate the issue and know where that performance pain is coming from, you're going to have the ability to, debug it yourself, to go to your vendor that's providing support and say, here's what we're seeing, how do we work through this issue? But isolating exactly where that pain is, exactly what's contributing to that latency, is truly the secret to most performance endeavors. And how long it takes you to get there, of course, is how long you spend working through the bug or the issue. In this case, we were seeing a couple of odd things where 113 millisecond latency on certain calls. Driving in, and in those calls, that was attributed to really waiting time, waiting on memory to be allocated. It wasn't disk I/O, it wasn't computational. So those types of characteristics that say, this is something that might be a configuration parameter that can be tuned. If I'm just waiting, there's often a parameter that's available to tweak and tune a cluster or an application to resolve that. And then if you have a little bit deeper insight, you can actually start to see some hotspots across the cluster. And you can say, by and large, are my requests largely bound by memory, by I/O, or is there something in between? Are we waiting on certain data to be returned? And so this type of analysis lets you know that cluster that was returning at 80 milliseconds, maybe the disk is slowing down. Maybe there's something happening, or if you're running on a managed service, maybe you need to provision more IOPS for just that particular node. You don't really understand the impact until you start to see that data distributed over time. And I think some of the other sessions today, you'll hear about war stories around how things over time, be it from tombstones, be it from other types of access patterns, start to change the behavior of your cluster, which was great when you first started it up. And then over time, it's going to take on very unique characteristics. But once you can identify it and understand where they are, you can start to make some decisions on the best way to resolve and possibly to change some of the data access pattern or where that data is being stored and provisioned from. It's also helpful to look across your cluster and look at some basic things like when is garbage collection running? When is compaction running? And if you can start to correlate that time in which compaction is running with some of your transactions, sometimes that's an immediate hit. You can do things like tune your garbage collection algorithm. So instead of running every so often and really impacting the cluster, you can run on a more regular basis. Likewise with compaction, you can schedule when's the right time to do compaction and make sure that during your critical time periods, if you avoid those things. So getting some high-level views into your cluster, again, some of these are out of the box when you think about that view of the end-to-end cluster. Others are a little bit tougher to get to, getting inside the individual transaction and understanding when this read request from cluster 3 takes 50 milliseconds. It's a little tougher to get to that level of detail, but this type of view is a great starting point and gives you that broad level view of what's happening over time within a cluster. And then you'll start to see things like, well, there's an interesting pattern here. We see, something like garbage collection giving us a lot of memory back, but it's a pretty big chunk, not a very, linear stair step here. It looks like it's happening on a fairly sequential basis. And also we're seeing, other patterns that you wouldn't necessarily want. A very large garbage collection running at, it was about 2 o'clock in the afternoon on the cluster. Likewise, a real spike in requests. So is there a behavior in my application that's driving, sort of that instant, hammering of Cassandra for some particular reason? Again, not by design, but things happen. Other things run against your cluster, and perhaps there's other traffic, a query that's coming in to do some type of report that just so happens to come in at the same time as your, high quality request that you need for real-time bidding. So when we had a chance to kind of do this end-to-end analysis with the client, we found a couple of things emerged. The reason that we were missing some of the SLA requirements around bidding, first there was some read time degradation that had occurred. There was a fair amount of data that had been written over and over to the same row, which was extending the row size and causing that row to span multiple system tables. Over time, and as some of that data was deleted, tombstones ended up building up and essentially really slowing down the data access for certain customers and certain requests. So not a guaranteed pattern to happen. There's lots of ways that you can experience that type of behavior, but it happened to be one of the root causes that they discovered was, well, a few of those data access approaches in those long reads across rows, as well as the delete operations they didn't realize they were doing on a regular basis, were causing some of those requests to just take quite a bit longer. Second one was around some of the coordination, and I mentioned the consistency level. They discovered that despite what they thought, there were some consistency levels of consistency all that as those nodes were queuing those requests, they would slow down and eventually time out. That type of timeout, of course, coming back ends up failing and giving them a block, so to speak, on their ability to deliver that bidding request. In this case, they discovered that while they thought a node was actually down, in fact, it was just timing out. And in some cases, it's better for a node to entirely fail. So be aware of environments where you might actually want the node to be killed when it has that type of behavior. And if you can model your application or modern some of your monitoring to look for those patterns, kill the node entirely, let it come back up, and don't have it sort of sit there in limbo holding up requests. And then lastly, the data sets that they were returning. They saw that some of those access patterns when they were retrieving requests were retrieving a much larger data set than expected. So again, it kind of comes back to it's not always a culprit within the application or within the database, but when you put those two together, you can see why the behavior application is really tied closely to the end-to-end performance of the system. And So you always want to be looking at, both patterns, both sides of the equation, and trying to solve for the right place where you're seeing latency and issues. Yes?
What is considered a very large data set?
It's a great question. I don't know in their case how large the actual size. I do know that depending on the type of request they were serving, they were keeping track of every request that was served to a particular user and type. In their environment, I'm not I don't know, but I do know they were appending the row, so they were adding data onto the row and letting that row grow, as opposed to storing additional rows or having some type of maximum value. So off the cuff, I'm not quite sure. They were a little, there's some specifics here that we couldn't share the full details. They didn't, like those transaction flows are close to what their application was doing, but they're not their exact topology and their exact discussion. So great question. There's probably some experts in the room that would tell you what's the biggest row size you should be dealing with or how many times to append, but I'm not sure what would be the best practice, and I'd hate to guess at that. Okay, the next application is one that actually that we've developed internally that one of our other division runs, that is basically watching around the world for outages and saying anytime there's an outage, can we figure out who are some of the downstream dependencies? So for example, when Facebook authentication login APIs go out, how many other third-party services are affected? And so it's kind of keeping track around the world, which gives you some insight when you're using your own application. If you're seeing a problem with page load, you can quickly say, well, is this a third party? Am I using a third party add, login, other type of service in constructing your page front end, and trying to understand are there multiple dependencies that could be in play here. Something that's out there happens to use a bunch of technology in the back end, including Hadoop, including Cassandra, to sample that data, put it in HDFS for long-term analysis, and to give some trending and reporting so that we can tell you how long over the last month was a particular authentication API down. I mean, as we know, the web is a very dynamic place, and it's often surprising to look at how many times there is a short outage that you may not be aware of, but depending on how you built your application, it could be directly impacted by it. So we looked at this and said, okay, we built this, and it's basically running every night and every hour a set of Hadoop jobs, basically MapReduce across the data set. And so we looked at internally, what's the behavior of our cluster? And see, these are some of the patterns that jumped out right away as we looked at that high-level view of the cluster. A couple things to notice when you look at the top left, CPU spikes like that. If you're used to any type of kind of massive parallel processing, you don't necessarily want lots of peaks and values. You'd like to have things fairly normally distributed so that I'm using as much CPU, bandwidth, and disk as possible. I mean, that's kind of a high-level view into the efficiency of, is my stuff working well? In a transactional system, maybe that's okay. You're going to have peaks and valleys depending on end user load. But if you're running in a batch processing, you really want that to be maximizing the capacity of that hardware. So that looked a little bit off. Looking at some of the network and disk I/O, a few spikes in there that are a little concerning to see a relatively consistent load on disk, but every now and then things get backed up, which probably correspond to some of the workload that's running on there. And yeah, overall CPU spikes. Memory. So when you look at memory utilization, across the cluster, an average memory utilization was around 30 to 40%, which if you're running jobs and you're keeping 50 to 60% of your memory free, again, one of those patterns that probably room for optimization. Maybe it's what's been written, maybe it's just tuning of the cluster itself. So a couple of things jumped out at that high-level view, but it didn't really give you insight into what was happening within the jobs themselves. In MapReduce, which is taking essentially a application and distributing parts of it to run across the cluster, understanding what those pieces are doing as they run, as they're tying up the cluster, gives you insight into, is that Hive query, poorly written? Can you tell your data scientist that, hey, this type of Hive query is really expensive, don't do that? Or if you're writing your own custom MapReduce code, is there areas that you can look at to say this is something that is really inefficient? And starting with that view that says, from the top down, here's what my cluster is doing at a macro level, here's all the jobs that are getting scheduled, and then within those jobs, there's a couple of different phases, mapping, shuffling, and reducing, which you can start to look at to say what's really going on behind the scenes. Getting a view of who's actually using your cluster. There's a couple of projects that let you do that. White Elephant from LinkedIn gives you an ability to kind of see the jobs that are running. There's also other tools that give you that end-to-end view in addition to a cluster view that can help you drive into them. We happen to build one, but there are multiple ways to do it if you want to kind of roll your own or if you want to have something that sort of provides that deep insight. We noticed that we looked at who's the biggest user of the cluster, because in most clusters you've got multiple jobs that are running. You've got a batch environment, so jobs get scheduled, they run, and they finish. So if you're looking at kind of a performance view of it, start with your biggest consumer. Don't start with a guy who's running a job once a day, once a week. Start with somebody who's really utilizing it a good amount. You'll get the most bang for your buck, so to speak, in trying to optimize what they're doing. Within the jobs, try to understand how much time are you spending mapping, shuffling, and reducing. That, of course, is the key to optimizing something like MapReduce, understanding where your time is being spent, how much data you're having to move between nodes, and ultimately, back to our kind of original thesis, why are we seeing such kind of peaks and valleys within the jobs? If you can identify inside particular areas, so understanding as part of the shuffle phase, one of the things that we noticed here is that as we analyzed the job and looked at CPU, disk, and network utilization, there's a third tier in there called wait. And that's your classic, you're waiting for memory allocation. You're basically waiting for the infrastructure to come back. And what we found during the shuffle phase was that there was a relatively large amount of time spent waiting for memory to be allocated. Now what that means as you start to dive in is once you can understand where that wait's occurring, you can say, all right, in this case, we're starting to see wait on the shuffle task, and I think one more detail here, we pulled it out, in these routines, job.shuffle, the input buffer, memory bytes, and parallel copies. Once you understand where that wait is occurring, then you can say, and in fact, sometimes once you get to that level of detail, you can Google that particular method and say, input buffer bytes, and you'll find a lot of feedback from, here's what things are set by default, but depending how jobs are constructed, we know defaults don't always work. And once you've narrowed down where that wait's occurring, then you can say, all right, well in this case, maybe I should increase the buffer size. Logically, if I'm waiting on memory in this particular part of the application, increasing the buffer size, or in this case, increasing the overall memory allocation for this step should help. And if you recall, we looked at the overall memory utilization in the cluster. We saw it was around 30-40%. We know we've got plenty of room. It's just a matter of figuring out which knob to tune to get inside there. By doing that, there was about a 65% reduction in the shuffle time because we were taking away that memory contention. So little tuning, little tweaks in environments that are heavily batch-oriented like MapReduce can make a big difference. Once we had moved beyond the shuffle phase, it was next time to look at the mapping phase. And in this case, it's one of the first steps that runs to really crunch the data that's in there. We found, again, there was a little bit of wait time, not as bad as before, but a relatively large amount of CPU time. And again, diving into another place where the mapper was essentially waiting for memory allocation, we found that the spilling thread and spilling buffer was ultimately contributing to it. So by increasing that buffer size and giving it a little more room, that eliminated the wait cycle. So little configuration tuning, in this case another 14% dropped out of the map time just by adjusting the buffers once we realized the behavior of the job. Again, context of what's my application doing. Hadoop is certainly different, and MapReduce is different than a pure Cassandra node access because you're running a lot more code in each particular node. So after these first set of fixes that were more configuration tuning, we found a couple of things. One, the CPU allocation looks a lot better, right? I mean, we're seeing much more normal distribution of I/O. We're not seeing spikes like we saw before. And overall, there's still a couple of troughs in when we go from the mapping to reducing. So areas that might still be improved. But overall, it's starting to look to a bit better from mapping and reducing inside. The next piece to take a look at was, it's a little hard to see here, but there's two parts of code within MapReduce. There's the framework, which we've been looking at so far, and then there's the custom code that you're running on top, either things that you've written directly, or if you're using some of the query tools, Hive, Pig, or anything that runs atop the cluster, they're generating that code that's going to run out there. So we're looking at some of the custom code that's running, and we see that, one, it's using the most amount of time, which is a good thing. It means we're not wasting a bunch of cycles on a framework, but rather the code that we've written is consuming the time. And more importantly, it's also CPU bound. So if we look at those three colors again, one was CPU, one was waiting, and the other was disk and network I/O. So kind of understanding the behavior of our application running across the cluster let us then start to dive in and understand, well, where are we spending time? I mentioned that in this case, there were a couple methods that were queuing up most of the cycles. And this happens to be a string algorithm that splits data. So as you go in and write code that is processing in parallel, string processing on that data is pretty common. And sometimes the decisions where you use a particular library end up chewing a lot of cycles. In this case, about 30% of our time was spent splitting strings, which doesn't really make sense. And so as you look at where that string split is occurring and what function you're using, you can then make an assessment to say, well, is this the right way to do it, and see what's really happening behind the scenes. The second one we looked at, and again, this was about when we looked at the overall kind of end-to-end, added about another 17% of improvement to the job. So each one of these chunks, because you're starting at the most expensive part, takes a pretty good cut at the overall experience. The last piece to take a look at was, again, we're now to a point where we're seeing a lot of CPU utilization, which is a good thing from a performance perspective. Anytime you have high CPU utilization, small code changes can make a big impact. Think recursion, think things that are just really impactful for an application. So understanding we're still CPU bound, not network bound or disk bound, is a good thing. And then moving on, in this case we had one other string kind of type routine that's comparing dates. And in this case we're using a resource bundle to look up and compare two date formats back and forth. And that date compare happened to load a dependency for resource bundles, which is part of localization. So it was doing a date compare based on the specific geography or whatever was associated to the JVM. That was in a very expensive way to compare two date objects. So by understanding here's an inefficient way to compare dates, is there a better way that preloads any locale-specific information? That little change added about a 70% reduction to the reduce phase in this case. Again, knowing where to look, understanding what's tying up your cycles, and then making an adjustment from it. So overall, we started off before we looked at our own code with a cluster profile that looked approximately like this. Again, we knew CPU usage was pretty good once we fixed the buffer issues. We knew that we were still running in about 6.5 hours, and there was still some behavior where our overall average really dropped off. In the end, it dropped down to just about 3.5 hours. So same hardware, same job, some configuration tuning, and 2 code changes to some string algorithms made a significant difference. You could have tried to throw more hardware at the problem, increase the number of clusters if you were running on the cloud. Sometimes that works, sometimes it doesn't, and it kind of brings you back to that scenario of what are you going to try first, and do you have some insight into where performance issues actually come from. So of note as well, some of the particular areas, about 6 times faster reduce phase. So you're not always looking at percentage gains, sometimes you're looking at order of magnitude gains. More important on a distributed system like MapReduce, where little changes affect the entire cluster, but certainly inside of Cassandra as well, small things can make a huge impact. Consistency levels, for example, make a pretty significant impact on the overall cluster. And again, we saw a much more normalized distribution. We saw kind of a nice trough get eliminated from the overall cycle. And as we look at the overall cluster profile, now we can feel a little more comfortable that we're running these jobs at scale and running them efficiently, kind of getting the most bang for buck out of that infrastructure, and that the team, whether it's the marketing team that's asking queries or the compliance team that's data mining, is able to put as much workload through the system. Overall, in looking at performance, it's always important to understand different components, but if you can get a view end-to-end within your system, you'll understand what really contributes to the end-to-end application. Sometimes it is a database configuration issue, sometimes there are challenges within the Cassandra cluster, other times it's really attributed to the pattern that has evolved over time in accessing or how that data has been distributed. So you'll find as you work more and more with newer technologies, there's always things that get discovered and fixed, and it is something that as you start to really understand what your usage and patterns look like, you'll be able to either improve or be able to go back to your vendor and say, here's where things are going wrong, can you help me tune or can you help me fix this particular access problem? Not specific to just Cassandra. If you're looking at any NoSQL database, you'll know as you start to use some of them, make sure you pick the right technology for the right job. and the different profiles that you have, be it transactional, be it read, write-based, you'll figure out which ones have the best performance for your environment. Cassandra happens to be a great fit for a lot of use cases. It's not perfect for everything. Doesn't mean you should get rid of Postgre or MySQL entirely, but for the right use case, it can be extremely performant for your app. And likewise, in the MapReduce world, understanding when things run in that distributed environment, it's a little bit different. And if you've got developers that are just starting to learn that kind of parallel framework, the impacts that they may not be able to see on their desktop when they run their job might actually end up being quite a bit different out in production. So little optimizations can make huge impacts when you run across a distributed framework, be it MapReduce or other parallel environments. With that, I want to kind of open it up to a few questions. I know it's been a bit of a broad view here into both NoSQL as well as Hadoop, but any particular questions or more importantly, maybe any insights that anybody would like to share with the audience here? Obviously, there's some experts in the room and some people that are just getting started with some of their projects. Questions?
What was the tool you use for profiling the Java performance in there?
Sure. So that tool was called that tool was called Dynatrace, and it provides the ability to look inside each tier in the application to get inside the job. There's some unique ability to go in and stitch together the transactions so that when you drop in, it happens to be agent-based, so think of it as a JVM library that loads on each node in the application, and then it discovers the application and gives you that kind of deep profiling capability. There's a pretty wide segment of tools in the APM market. There's things that have been built. I spent 10 years at IBM building software and never used an APM tool because the one we have in-house, it just wasn't easy to use from a development perspective and was very heavy to instrument. The company that I joined actually has a best-of-breed tool, and so what's been really interesting is to see the ability to kind of drop in, discover an application, profile, be it a Cassandra cluster or a Hadoop cluster, and really get that same insight that you'd be used to running on a desktop profiler, but running in a production environment. So that's essentially what we do. I've tried to keep it not too much of a product pitch here to recommend some best practices. There's a lot of ways that you can extract some of this data yourself. I mentioned Ganglia, Nagios give you some views into it, but as you start to look inside the job, that's really where the investment around sort of APM gives you that out-of-the-box insight into what's really happening in my code, what's really happening in my cluster, and sort of gives you that one-click analysis that is highly valuable if used properly. Any other questions? Quick poll. How many people have written and have a Cassandra or NoSQL application running in production or maybe coming into sort of a production by, say, the next 3 to 6 months? A couple? Oh, good hands. All right. And what about on the Hadoop and MapReduce side? Hadoop as well? A little bit. Okay. And what about using MapReduce on top of, say, DataStax Enterprise on your Cassandra data? Has anybody started to do that yet? A little bit? And what's been your experience so far? Is it working? Is it something that's valuable on top of the data set that's in there?
It's interesting, right? You have two completely different systems. You have Hadoop for batch processing, you have Cassandra for real time, and finding use cases for the two is it's something that you have to actually look at. Does this make business sense to actually go through with this?
Okay. Cool. Well, with that, if you'd like to learn any more about Dynatrace, we're certainly happy to show you a bit more. We're down on the exhibit floor. Any other questions around some of the customer use cases here? I'd be happy to answer as well. But thank you very much for your time, and if you guys have a question, feel free, we can chat. I'll stay right here.
I don't have a question per se as a comment from earlier about when growing out the size of your roads. The hard limit on that is 2 million columns.
Okay.
You never want to reach that level though. If I remember correctly, and someone in the audience will know the reason for this, but you want your entire road to be able to fit into memory at the very, very least. And so whatever between 100, 1,000 rows to like 10 million or so, that the answer is probably somewhere in there.
somewhere between 2 billion and 100,000.
Oh, no, no, well, no, but not close to 3 billion.
Okay. Cool. There's your answer. Like I said, there are experts in the room here, and certainly you've got a lot of experts. Experts around the show. Thank you very much. And